quickly tell you, we started in perturbation theory. Yeah, so it started on perturbation theory. So the important thing was, when you solve the Schrodinger equation, the important thing was to identify a, just a minute. Bluetooth off, yeah. Sorry, just 1 minute. My Bluetooth was off, so okay, now it should be all right. Yeah. Okay, you can see the screen, right? Yeah. Hello?
Yes, sir.
Yeah. So when you solve the Schrodinger equation by perturbation theory, important thing is to identify a zeroth order Hamiltonian whose entire solutions are known. So we give the quantum numbers in the subscript I, and the superscript 0 tells you that these are the solutions of H naught. And then those eigenvalues are ordered in the following manner, that the zeroth state is the lowest state, then first state, and second, and so on. So then we look at the full Hamiltonian, which differs from H naught by the perturbation. And ideally, this perturbation is very small. And then we assume that as the perturbation is applied, the ground state solution of H naught assumes the ground state solution of H. So that's the idea, because we are only interested in the ground state. Okay. So, but you will still see later that we require all the solutions of H naught. I'm again repeating, because you might wonder that why am I looking at all the solutions of H naught if I'm only interested in the ground state solution. All right, I'm only interested in the ground state solution for H. So again, for the H also there is an ordering. So of course I'm interested only in E naught, which is E naught and psi naught. And the desirable thing was that H naught is a dominant part and the solutions of H naught be completely known, and so on. So to start the perturbation theory, this was our main thing, to construct an imaginary Hamiltonian with the lambda as a parameter, such that the Hamiltonian is H naught plus lambda v. This Hamiltonian is quite a flexible Hamiltonian, in the sense that at lambda equal to 0, this assumes the zeroth order Hamiltonian. At lambda equal to 1, this assumes the physical Hamiltonian H. So in a way, going from H naught to H is switching the lambda from 0 to 1. So that is what, switching the lambda from 0 to 1, I move with one Hamiltonian from H naught to H. So that was the idea that we said. So we are now looking at the solution of this general Hamiltonian in the following manner, using very similar notation. So now we don't use 0 in the superscript, because this is for the full Hamiltonian H. And then we say that obviously at lambda equal to 0, this is psi I 0, because these are the solutions of H naught. Similar thing is for EI. And at lambda equal to 1, they assume the exact functions. I hope that is clear, right? Then by construction, we write psi and E as a function of lambda by a power series. It can be a Taylor series in which there will be factors coming in, but assume that power series. And in particular for the ground state, we write this and plug them into the Schrodinger equation. I remind you that at the end, lambda would be equal to 1 for my exact physical Hamiltonian. So obviously, the physical Hamiltonian would be a sum, the energy would be sum of all these, and we know this zeroth order to begin with. So these are called the corrections, first order, second order corrections to the energy and the wave function. Ideally, of course, at low order, the result should converge. So ideally, what should happen that when you're doing this perturbation order, the m plus 1th order energy for the ground state should be lower than mth order absolute value. Of course, the absolute value, because there is an oscillation, positive or negative, that I cannot tell, but eventually they should converge at some reasonable order of perturbation. Then what we did with this power series expansion, we plugged that into the general Schrodinger equation and then equated the powers of lambda, and that is how we got the different orders of perturbation. So this is the lambda to the power 0 equation, which is zeroth order Hamiltonian. So of course, this is nothing new. We just find out the zeroth order Hamiltonian, the ground state solution for the zeroth order Hamiltonian. Then you have the first order perturbed equation, and you can see that there are always two terms on the left hand side, because H of lambda has only first order in lambda, although this has power series. So obviously this will be up to second order, up to first order, here also up to first order. At the second order onwards, I find that although this has two terms, in the right hand side, the terms, number of terms keep on building, and it becomes, number of terms becomes 2. So at the nth order, this will become n terms. So they really start by 0th order of E, nth order of wave function, and so on. Increase this order, decrease this order. The sum of order should always be the number, what I'm looking at. So 2, 3, whatever. So this was the general nth order equation. As you can see, psi 0 n, v psi 0 n minus 1, because this is first order in H, first order in lambda. And then you have 0 n, 1 n minus 1 up to n 0. Okay. So this can be written in a different form by transferring terms for each order of psi 0 on the left hand side. So you have h naught minus e naught 0, psi 0 n plus v minus e 0 1 psi 0 n minus 1, and so on, minus this. In a way, this is a transcription of the Schrodinger equation in the following manner, that I now take nth order of this equation. So 0th order of this, nth order of this, first order of this, n minus 1th order of this, then second order of this, and then you remember the second order does not have any contribution from H, so it has only minus E naught 2, minus E naught 3, and so on till I hit the 0. I also propose that the way I wrote it, the psi 0, 0, psi 0 is 1, provided all the correction terms are orthogonal to psi 0, 0. So this is exactly what is called the intermediate normalization. And I specifically said that we are following the Schrodinger perturbation theory. And in actual practice, what would be H naught would be decided by partitioning of H to H naught plus V through what is called the Euler-Placet partitioning. And that second order will actually give the first value of the correlation energy. We'll see that later. And that is why it is called NP2. All right. I think with that, I will move to today's slide. Okay. If there are any questions, meanwhile, you can still ask. This is okay. So let me look at the salient points that I put H equal to H naught plus V. That is very important. And this is the dominant part. And this is small. Okay, whatever it means. That we can discuss a little bit later. A more general Hamiltonian for which we write down the perturbation expansion was H of lambda as H naught plus lambda V. That's a more general expression. The more general expression of the Hamiltonian for which we had fitted. And from here, by equating powers of lambda in the Schrodinger equation, which is H minus E psi equal to 0, I can get a general nth order equation. Okay? And at the end, my psi 0, ground state psi 0 would be psi 0, 0 plus psi 0, 1 plus psi 0, 2, etc. Provided each of these correction terms, so psi 0, 1 with exact, with the ground state, with the 0th order state is equal to 0. So psi 0, 2 similarly with psi 0, 0 is 0, and so on. You can see that I have a situation where psi 0, 0, psi 0 is equal to 1. I hope you can see this. You can easily prove this, because if I expand this, I will have the first term as psi 0, 0, which is 1. The next term would be psi 0, 1, which is 0. Next term would be psi 0, 2, which will be 0. Of course, when I'm writing this, remember the other way of writing is also, complex conjugate is also true. Okay? So this essentially conforms to the intermediate normalization. I hope you remember the intermediate normalization. It had two important components, that this was equal to 1. That means the zeroth order or the most dominant part overlap with psi naught exact state is equal to 1. And all corrections are orthogonal to this dominant part. So that this relation is also holds good. So no correction I'm going to apply here. And that is something I have to remember, which will have an overlap with psi 0, 0. Then this is my choice. And that will conform to intermediate normalization. So that is what we will remember when you start correcting. Let me now come to the first order equation. See, you remember for the zeroth order equation, I don't get anything extra. I already know that is the solution of H naught. I come to the first order equation and I try to write from here now directly. How do I write the first order? Zeroth order of this, first order of this, plus first order of this, zeroth order of this. I hope it's clear. I'm writing only for the ground state. So H naught minus E0, 0. This is zeroth order of H minus E naught into acting on psi 0, 1 plus first order of this, which is V minus E0, 1 acting on psi, or V minus E naught 1 with psi 0, 0, and this is equal to 0. Okay? So that's my Schrodinger equation. H minus E psi equal to 0. I hope it's clear. Everybody can see this very easily. It's a first order equation. Total order for each term must be 1. Because they must all conform to the lambda to the power 1. Is it clear to all? Yeah, please tell. Before I proceed, I want to hear from at least 1 or 2 people.
Yes, sir, it's clear.
It's clear. Okay, good. Now our task would be to solve this equation. And if you remember, I said these are the terms which are not known. Please remember. Rest everything is known. H naught and V are known by construction. How we will construct, we'll come to that for this particular problem. But having done this, my job is to now construct this. All right. So let me now do a trick. Project this equation by the dominant part of psi 0, which is basically psi 0, 0, which means the ground state solution of H naught itself. So I write projection. This is an equation. So of course, when I project, I multiply by the conjugate and integrate. So they all become numbers. Right now, they are not numbered. They're actually equations. H naught minus E0, 0 psi plus, just please follow this carefully. V, I'm just doing nothing actually, just writing psi 0, 0 star and integrating. Is it okay? Now they are all becoming numbers now. They're integrated quantities. So complete integral, definite integral, so they are all numbers. I hope all of you can follow from this to this step. Any problem, you just let me know. Now you look at very carefully. This term, whatever is the value of psi 0, 1, I don't know. But what I'm trying to say that this particular term or this vector, the conjugate of this vector is 0. Can you see this? Because H naught minus E0, 0 acting on psi 0, 0 is 0. Because this is a solution of H naught with an eigenvalue is not 0, right? So this quantity is already 0. So this is a 0 vector. It's a conjugate of the 0 vector. So irrespective of psi naught of 1, this is going to be 0. This integral is going to be 0. Because it's an integral of psi 0, 1 with a 0 vector. Null vector. So that's the result is going to become 0. So I have only this term. So then I can write this equation as psi 0, 0. Now I break it out. V psi 0, 0. This is a number. This was an operator, but this is a number, E naught 1. So that can come out of it. And psi 0, psi 0, psi 0, 0 is 1. Of course, that is not part of the intermediate normalization. That is part of the normal normalization. So that's equal to 0. And lo and behold, we have a very simple equation for the first order correction. So the first order correction is merely an average value of the defined perturbation operator with respect to the 0th order ground state of H naught. So this is already known. This is also known. So you have to do nothing, just integrate this. It's a definite integral. And you get the first order correction to the energy. So it is that simple. Is it okay? If there's any question, please ask. At any point, if there's any question, please ask. Okay. So now I already have E0, 0 to start with. I now got E0, 1. So let me see what is the sum of these two that I get. What is E0, 0? It is eigen solution of H naught, which I already know. And I can write this as psi 0, 0, H naught, psi 0, 0. Right? I hope all of you can see this. Plus E0, 1, which I can now write psi 0, 0, V psi 0, 0. So it's an average over V of V with respect to psi 0, 0. This is an average of H naught with respect to psi 0, 0. Of course, this is eigenfunction. So I need not have written as an average. E0, 0 is the definite number. So what is the sum of the 0th and the first order analysis? And that is very interesting. Now both left and the right hand side, I have a psi 0, 0. So I can simply add the operator. So I have psi 0, 0, H naught plus V, which is H, psi 0, 0. It's very interesting. It tells me that this is something that I already know. I have the Hamiltonian, physical Hamiltonian, which I break up into H naught plus V. Irrespective of how I broke up, 0th plus first order is nothing but the average value of the physical Hamiltonian with respect to the ground state solution of H naught. So this is where the breakup will matter, because this value, this will change. So depending on how I split H naught, this value will change, this function will change. But then once I have done this, I know how to calculate 0th and first order. I don't actually need 0th and first separately. I can directly get the sum, which is the average value of the physical Hamiltonian in this state. Remember, this state is not an eigenfunction of the Hamiltonian. I want to again repeat. This state is not an eigenfunction of the physical Hamiltonian. It's an eigenfunction of H naught only. So this is truly an average value. Okay? So you have to just calculate the average value. Given this psi 0, 0, you have to just calculate psi 0, 0 star, H, psi 0, 0 d tau. It's a definite integral. And that is going to give me 0th plus first order. And you will see its significance very soon when I define H naught, because that will define me the psi 0, 0. And you will realize why in actual quantum chemistry, we never talk of first order correction. Because I will show you later that I can define my H as H naught plus V such that the ground state solution of H naught is nothing but the Hartree-Fock function. And if it is a Hartree-Fock function, this is nothing but Hartree-Fock energy. This is Hartree-Fock, H. If you remember, the Hartree-Fock energy is the average value of H over the Hartree-Fock function. So this is already a Hartree-Fock energy, which is actually different from the 0th order energy. It is sum of zeroth and first order, and hence no correlation energy appears at this stage. If I make a partition of H as H0 plus V, where the solution of H0 will be Hartree-Fock, the ground state solution of H0 will be Hartree-Fock function, not the energy, but just the solution. Energy will be different, but the sum of energy of the zeroth and first order will automatically become Hartree-Fock energy. And that is the reason we always call that the correlation energy starts from second order. This particular partitioning that I'm talking was used by Euler and Placet. Of course, in another crazy partitioning, you can have a first order, because this will not be Hartree-Fock. Right? Then you can have a first order correction. But if you make this Hartree-Fock, and that is very easy to do, that is what Euler and Placet did, you don't have any correction at the first order, and the correlation energy starts at the second order. So basically, let me write this. That Euler, I will tell you the partitioning a little bit later, but let me just say that Euler and Placet partitioned H as H0 plus V such that the ground state solution of H0 is the Hartree-Fock determinant. How to do that? There are multiple ways of doing that. I will come back to it later. It's just a single determinant. I will come back to this later, but this is the basic idea of the Euler and Placet partition. And if this is so, then I can clearly write that the zeroth plus first order correction energy is nothing but the Hartree-Fock energy. Remember, zeroth itself may not be Hartree-Fock energy, because zeroth energy is just this, where it is not H, it is H0. And this is somewhere many people get confused. This is Hartree-Fock, all right, but this is not the physical Hamiltonian, this is H0. So this need not be Hartree-Fock energy, but some is. Because remember, always the Hartree-Fock energy was psi Hartree-Fock star H psi Hartree-Fock, physical Hamiltonian. Okay? Hence, zeroth plus first order in Euler-Placet partitioning is Hartree-Fock energy, and hence correlation, that is further improvement from Hartree-Fock, starts only from second order. And that leads to MP2. The first correction to Hartree-Fock is MP2. Is it clear? Hello?
Yes, sir.
Okay.
So, sir,
Yes.
I mean to say, like, if this H0, like we are splitting H is equal to H0 plus V. So
Yes.
if this H0 wasn't the Hartree-Fock Hamiltonian, then
No. 1 minute. That's a different matter. There could be another way of making ground state solution as Hartree-Fock, even if it is not a Hartree-Fock Hamiltonian. You have already read what you mean by Hartree-Fock Hamiltonian, but there are other ways of making it. I'm only saying that if the ground state solution of H0 is the Hartree-Fock determinant, then obviously this sum total is Hartree-Fock energy. Right? But if it is not, then of course it is not. So what is their question now?
So this psi 0 belongs to some Hamiltonians, eigenfunction of some Hamiltonian H0.
H0, yes, right.
So what is that H0?
Like, I will come to that.
Okay, sir.
Okay, I will come to that. So I am merely mentioning. See, please see I'm going in a sequential manner. I have now mentioned that the Euler and Placet partition H is H0 plus V, such that, please try to understand, that the ground state solution of H0 is the Hartree-Fock determinant. That is all I mentioned. How was the partitioning done? That will be seen later. But the second part, that such that the ground state, that is what I am now emphasizing. And if that happens, the zeroth and first order is equal to the Hartree-Fock energy, and hence in that partitioning correlation will start from the second order. And this will be called MP2. Is it clear? What you are asking is how to get H naught such that this will happen. This I will come a little later. Okay? All right, can I proceed? So I can go back to the first order equation once again. And now I said that I already know this. I don't know this. Okay? Before I know this, let me go to the second order equation and see what I need to know for the second order correction, because that is very important. So let me go to the second order equation and let me write the second order equation once again in a very easy way. Psi 02 minus E02. I hope all of you are on page with me. So 0 plus 2, 1, 1, 2. So there is nothing coming from the H, so it is minus E02 psi 00. Is it okay? And now I do the same strategy. Project this with psi 00. Minus E02 psi 00 psi 00 equal to 0. So I hope all of you are with page. What I have done is the equation I have transformed into numbers with every time I have multiplied it, each term with psi 00 star and integrated, including this term. Is it okay? Is that all right? Can I proceed?
Yes, sir.
Now, by using my argument earlier, this term again goes off. Because this is 0. Right? Exactly the same argument. Doesn't matter what is there in the right hand side. Previously it was psi 01, now it is psi 02. This is of course 1. So it's a Hartree-Fock determinant. So it normalized to 1. So what I now get is this minus E02 equal to 0. So then I get psi 00. So let me write this again. V. And now I'm splitting this term. Psi 01. Remember, for the first order, it was psi 00. So that is how I got E01. But here I have one more term. Minus E01. Psi 00. Psi 01 now. This was psi 00, remember. And then minus E02. This is where psi 00, psi 00 comes equal to 0. Is it okay? So I have simply split up these terms as two terms. And now you can see, because of the intermediate normalization, I told that my choice is that all corrections are orthogonal to psi 00, right? So this actually goes off, leading me to an expression which is just like E02, E01, but now it is E02 is psi 00, V psi 01. Contrast this with E01. I write it on the bottom. E01 was psi 00, V psi 00. So what is the contrast? You can see that instead of 0, it just becomes 1. And that is obviously because here 1 here, 1 must come from here to make it 2, or come from here, either side. The way I have done, it is coming from the right hand side. And here you don't require because this already has an order of 1. Is it clear? So to understand how to get E02, now I need to know psi 01. Remember, for E01, I am again repeating. For E01, I do not require psi 01. And this is a very interesting part. From the zeroth order wave function itself, I can construct E naught 1. But for E naught 2, I don't require psi naught 2. I require psi naught 1. So one of the important thing is that any nth order correction, and this is generally true, to energy does not require the knowledge of nth order wave function. You actually require lower order knowledge. I will come to a very important theorem that Epstein had done, that is called the Epstein's 2n plus 1 rule. I will not prove, but I will simply state. So, but it is important to realize that from a lower order wave function, I can always construct higher order corrections. This is a very important thing, that the energy is always calculated more accurately than the wave function. So, so to say, energy is calculated more accurately than the wave function. I hope you understand the meaning of this statement. That is, I know wave function only up to first order, but energy I know up to second order. So this is more accurate. In a way, this is an advantage, because to get higher order E naught, I need not to get dirty my hands in terms of wave function. So in this case, I have only the first order correction to the wave function. Now, my task is, how do we find out the psi naught 1? If you remember, the psi naught 1 first appeared in the first order equation, right? First order equation, I first had psi naught 1, which is psi 0, 0, this psi naught 1. So this is where it appeared. So I need to address this problem now. So to do this, let me now go back to the first order equation. Again, you should be able to write the first order, second order very easily. First order equation, you can see from here itself. If I make this psi naught 1, if I make this psi naught 0, if I eliminate this term, it's a first order equation, right? Because this becomes one order. This also becomes one order, because already one order is there. So this has to be 0, and this is not there. Correct? So I go back to the first order equation as H naught minus E0, 0. Please remember, you should not see it. You should write it, think and write. Because there is H minus E psi. So think and write. So this is 0th order. So this must be first order. Plus, this is first order. So V minus E naught 1. This is 0th order. Equal to 0. So that's my equation. I can use a Ket function. That's the immaterial. And now I calculated, by projection of psi naught 0, I calculated E naught 1 already. But now I want to calculate psi naught 1. So psi naught 1 is a function. E naught 1 is a number. So we have to be very careful how to do this. Yet, one important thing I know, that is psi naught 1 by intermediate normalization is orthogonal to psi naught 0. Remember that psi naught 0 is orthogonal to psi naught 1, or vice versa. So that is something that I know. To find out psi naught 1, now what do I do? I would use an expansion in a basis. And this is why it is very, very important to understand in a basis. So what basis do I take? I have to also ensure this. So the basis that I can take is very conveniently the basis of H naught. Right? I have the H naught eigenfunction. So if I take this basis, That's a very good basis, ensuring that this does not contain psi naught 0. So how do I do that? I essentially then expand psi 01 as a linear combination of all functions of h naught except I not equal to 0, ci psi I 0. I hope you understand what I meant now. So eigenfunctions of h naught form a complete basis. So I can expand this in terms of complete basis, but I know that the overlap between psi naught 1 and psi 00 should be 0. So that is excluded because this is basically the overlap coefficient that you can see very easily in an orthonormal basis. And also remember, all the h naught eigenfunctions are orthonormal to each other because they are eigenfunctions of a Hermitian operator. Of course, h naught is Hermitian. There is no doubt. You can see that what are these coefficients. So let's say I take a kth coefficient, so I equal to k. What is the value? It is very easy to see. That is equal to psi k0, psi 01. I have done expansion only for psi 01 because I'm interested only for ground state. You can very easily see if I expand this in terms of all the eigenfunctions of psi I0, since they are orthonormal to each other, all of them will vanish except when I equal to k. And when I equal to k, the result will be ck. Can you see this? I mean, this is something that you have done many times in quantum mechanics. I'm again repeating. So any psi k0, psi 01 overlap of a kth function with psi 01 will give me these coefficients. For the reason that it is intermediately normalized, I've avoided using I equal to 0. The reason I'm expanding only first order wave function, I will keep a tab that this is the first one, superscript 1. Because later on I may require to expand second order, third order in the same manner. So every order I can expand like this, except that the coefficient will be different. Is there any question? Please ask me. So this is what I am doing. Just like many differential equation solution I had done, power series expansion. So similarly, I am taking a complete basis set expansion. In a way, power series expansion is also a basis set expansion, right? So what I need to know for psi 01 now, these are already known. I need to know these coefficients, right? Which means I need to know these numbers. These are the numbers which I need to know to evaluate the coefficients for all k. For all k I need. Of course, k is a special number, but I is a dummy index, so it doesn't matter. You understand what I mean. In some sense, if I put this here, I can write psi 01 as a sum over I not equal to 0. And now, because of ci1, I'm going to write this as I. So I can say this is, first I will write this, psi I0, and then ci1, which is psi I0, psi 01. Please note, this is a very special way of writing. I first wrote this, and then I wrote ci1 as psi I0, psi 01. So I'm writing psi 01 as sum over I, psi I0, psi I0, psi 01. And hence I can say this is an operator which is acting on psi 01, and it is called an identity operator. Because this operator acting on psi 01 gives me back psi 01. So this is a very special way of looking at it. So I can say that in fact in any complete basis set, if you just do psi I0, it is equal to 1. 1 means identity operator. Remember, this is very different from writing integral. Integral, I write ket and then a bra. This is ket and then bra. Sorry, in the integral, I write bra and then a ket. Here it is ket and then bra. So this is not an integration. This is actually an operator form. If you sum over all states, it is equal to identity. Here, very specially, I equal to 0 need not be there. But within the intermediate normalization, now this represents an identity operator. Just remember this. I mean, it's not important, but a lot of things can be done by such thinking. Many times they are also called resolution operator. So this is a resolution operator to get the identity. In any case, what I now require is a solution of this psi k 0, psi 0, 1 for all k, and then I'm done, because then I get the ci1. I already know this. I know the psi 0, 1, right? I'm done. So I come back to the first order equation here. This is my first order equation, and try to get psi k 0, psi 0, 1, right? That is what I'm going to get, psi k 0, psi 0, 1. So how do I get psi k 0, psi 0, 1? I will project this with psi k 0. That's the best way to do. Remember, initially when I got E0, 1, I projected with psi 0, 0 star and integrated. Now I'm going to project a kth function of H0 and then integrate. And now we very easily see why I need all solutions of H0. Because of this very fact that I'm going to expand in the solutions of H0. So I required. So let me project that first order equation with psi k 0. So psi k 0, H0 minus E0, 0. This is still the ground state. So remember, since this is ground state, this remains E0, 0. This will not be k. Only here psi k 0 will come. And then you have a psi 0, 1 plus psi k 0 V minus E0, 1 psi 0, 0 equal to 0. Is it clear? It's the same equation that I wrote, but I had put 0. Because I have written k, remember now this term cannot be cancelled, because this is not 0. Why it is not 0? Because here it is E0, 0, here it is psi k 0. So what will be this term? You can see if I allow H0 to act on psi k 0, and it is just the left vector, it will be Ek 0, psi k 0. So if I write this will then become Ek 0 minus E0, 0. Then you have the psi k 0, psi 0, 1. I hope you can see this. It's very easy to simplify this, because this is psi k 0, E0, Ek 0. So Ek 0, psi k 0, the left side of this. And of course, minus E0, 0 is there. And for each of them, that is psi k 0 is already there. Each of them I have a psi 0, 1. I hope, can all of you write this now from this to this term? When it was k equal to 0, it was 0 because this was 0. So this cancel, E0, 0 minus E0, 0, right? Can you see this? The first line? Hello? Can somebody
Yes, sir.
say? Yes, yes. So psi k 0, then I write the second term. Psi k 0, V minus E0, 1, psi 0, 0 equal to 0. What I wanted exactly is psi k 0, psi 0, 1, right? And that is what has come out here. So that's my ck1. That's the coefficient I'm looking at. So my coefficient, and of course here there are two more terms, this minus this. But very quickly you see the second term does not survive, because this is a number and psi k 0, psi 0, 0 are orthogonal. There is a separate orthogonality. That is the orthogonality of H0 states. And remember, I am not interested in k equal to 0. I am interested only for I not equal to 0. So k not equal to 0, right? So of course I should write that k is not equal to 0. So this will never become 0. In which case, these are ck1. So since this is orthogonal to each other, I can write my equation in the following manner. Ek0, I can simplify it, minus E0, 0 into ck1. I'm just writing this coefficient now, plus psi k 0 V psi 0, 0. Remember, I wrote it separately. And minus E naught 1, these are orthogonal because k not equal to 0. So that vanishes, it is equal to 0. Is it clear? For every k, which is not equal to 0, k equal to 1, k equal to 2, all excited states basically, of H naught. That will give me the ground state first order correction. That's very interesting. So to get the ground state first order correction, I'm utilizing the excited state solutions of H naught. So that's the basic philosophy. Now I can very easily write CK1. So CK1 is this quantity, psi k0 V psi 0, 0, divided by this quantity but with a negative sign. So I will write this as E0, 0 minus EK0. I just change this sign and I'm done with. Note that this cannot be done for k equal to 0 because this will become 0. You'll get infinity. Of course, that is only because you're not supposed to do this, right? And remember, when k was equal to 0, this numerator was nothing but E naught 1. The numerator was nothing but E naught 1. Here, the same thing has come in the numerator for CK1, but divided by the energy difference. That is very important. So for every k, I will calculate an integral. This is now an integral. This is not an average value. Integral of V between 0th state of H naught and the kth state of H naught. Both are H naught states. I know them. Divide by the H naught energy differences. In this manner, 0th minus k. So the denominator is always negative because E0, 0 is always less than or equal to EK0. And that will bring me now to write psi 01. So I can write psi 01 equal to, remember it is sum over k, ck1, psi k0, right? And I write in the same manner for psi k0. Of course, k not equal to 0 or I not equal to 0, it doesn't matter, k not equal to 0. I write psi k0 first and then I write ck1. What is ck1? Same thing with psi k0. V psi 0, 0 divided by E0, 0 minus EK0. Note that you may be tempted to tell me that this is again identity, right? It is very same as I discussed here, that the identity operator is nothing but psi k0, psi k0. Somewhere I said this, right? From this expansion of psi 01 with respect to psi 01. So you may be tempted to tell me this is an identity. So can I write this as V psi 00 divided by this? No, you cannot, because this sum over k includes the denominator. The k is in the denominator. I hope you can see this. The k is the denominator. So I cannot sum the numerator separately. I have to sum this whole thing. And this is actually called a resolution operator. So it is called something like a resolution operator in terms of H naught eigenfunction. Sum over k not equal to 0. This has a different meaning. Psi k0, psi k0 divided by E0, 0 minus EK0. It's also an operator, but a resolution operator acting on V psi 0, 0, such that this only simplifies my writing of psi 01. So psi 01 becomes this resolution operator R0 V psi 00. It's very easy to write. All right. What we now will do is to plug this psi 01 onto E02. And we will get the result. Okay. I will do that on Thursday, because I have a meeting now. So I will complete this on Thursday. And then I will come back to the H0 partitioning. Moeller plus partitioning that we discuss. After that, it's very easy to write down. And we'll close the perturbation theory with that lecture. Okay. So if there are any questions, please ask on Thursday. Thursday, 9 o'clock, I'll come. And then we'll discuss this. Because I have a meeting now, so I have to leave. But if are there any quick question, I can still take. All right. If not, then I will leave today. I don't know if Madam is there. Can you see?
Yes, I'm here.
Yeah. Okay. So Sangita, I'll leave it to you. Yeah. Yeah, I think I have stopped sharing.
You can stop this recording here. We'll start again.
Okay, you can stop the recording. Yeah. Okay. Then I'm leaving now. Okay. Okay. Thank you. Thank you.